This presentation is part of the TI in Focus AP Calculus video series. In this video, I'll discuss the solutions, relevant concepts, and the scoring guidelines associated with some of the parts of our 2020 mock AP Calculus exam, Form BC, Question 2. My name is Steve Kokoska. I'm a recently retired professor at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. Form BC Question 2 involves a particle moving in the plane. Its position is given by a vector-valued function, x of t, y of t, at time t, where t is measured in seconds, and x and y are twice differentiable functions, both measured in meters. We are given a symbolic expression for the derivative x prime of t, and we also have selected values of y prime of t given in the table. And in addition, we know that the position of the particle at time t equal 12 is 4 minus 3. In part C, we need to use Euler's method with 4 steps of equal size to approximate y of 4. And just a reminder, in the context of this problem, y of 4 is the y-coordinate of the position of the particle at time t equal 4. Well, the key concept here is certainly Euler's method. So here's some background information and a visualization of Euler's method. The goal is to find a numerical approximation to the solution of a differential equation. And the basic idea used to generate slope fields is used to find this approximation. Let's consider a specific initial value problem with y prime equal to 2y minus x and y of 0 equal to 1. If we use this differential equation, then y prime of 0 is equal to 2. So we know the solution curve has slope 2 at the point 0, 1. So a first approximation to the solution could be the linear approximation. In this case, it would be L of x is equal to 2x plus 1. This is an equation of the tangent line to the graph of the solution at the point 0, 1. Here's a graph of the actual solution curve and the first approximation. You can see that as we move farther away from the starting point, the approximation becomes worse. So it makes sense to stop after a short distance along the tangent line and make a correction. So we can improve our approximation by traveling only a short distance along the tangent line, and then making sort of a mid-course correction. And we should change direction as indicated by the slope field. This graph shows what happens if we start out along the tangent line and stop when x equals 0.5. The horizontal distance that we travel is called the step size. Since L of 0.5 is equal to 2, then an approximation to the value of y at 0.5 is 2. So let's take this point, 0.52, as a new starting point for a new tangent line. If we use the differential equation, then y prime of 0.5 is 3.5, and the new tangent line is L of x is equal to 0.25 plus 3.5x. For x greater than 0.5, we can use this new tangent line as an approximation to the solution, and this is the maroon segment in the graph. Note that if we were to decrease the step size, say from 0.5 to 0.25, it seems reasonable that this procedure would produce an even better approximation. Now, let me describe this method in general. Start at the point given by the initial value and travel in the direction indicated by the slope field. Stop after a short distance and look around. Consider the slope at this new location and travel in this new direction. Continue in this manner, stopping and changing direction as dictated by the slope field. This procedure will certainly not lead to an exact solution to an initial value problem, but it does provide an approximation. And it seems reasonable that if we decrease the step size, that is, the number of mid-course corrections, then we would get a better approximation to the exact solution. This figure illustrates Euler's method in my example with a step size of 0.25. The approximation seems closer to the exact solution, better than when we used a step size of 0.5. Here's a formal statement of Euler's method, and just a little bit more notation. We can find approximate values for this initial value problem with step size h at x sub n using this expression. And this is exactly what we did in our example. We traveled just a short distance along the tangent line as determined by the slope field or differential equation to arrive at a new or the next approximation. Let's take a closer look at this method. First, it's certainly possible for the step size to be negative in Euler's method. For example, h could be minus 0.1. In this case, Euler's method is used to approximate values for the solution of the initial value problem to the left of the initial value. We have seen graphically, and again it seems reasonable, that if we use a smaller step size, we would arrive at a more accurate approximation. And some find it easier to remember and apply Euler's method if Leibniz notation is used. In this case, let the step size h be equal to delta x, and use Leibniz notation to represent the derivative. This is the resulting expression for y sub n. Now we're ready to solve this problem using Euler's method. The initial value given is y of 12 is equal to minus 3. And the derivative here is y prime. And note that this is a function of the independent variable t only. In this problem, we need to approximate y of 4 in 4 steps. So, since we're starting at t equal 12, the step size is h is equal to minus 2. The first approximation is y sub 1, equal to y sub 0 plus h times y prime of t sub 0. Remember, t is the independent variable here. Y of 12 is equal to minus 3. That's the initial value. The step size is minus 2, and y prime of 12 is equal to minus 5 from the table. So the first approximation is y of 10 is approximately 7. Here's the next step. We use y of 10 equal to 7, the step size of minus 2, and y prime of 10 is equal to minus 1 from the table to help make a mid-course correction. Y of 8 is approximately 9. We continue in this manner. Here's the third step, and here's the fourth step. So, using Euler's method with 4 steps, we found that y of 4 is approximately 7. Here are the scoring guidelines for this problem. Part C was worth 2 points. The first point is a conceptual point for conveying an understanding of Euler's method by presenting the correct first step. And the second point is, bluntly, for everything else, but more formally, for the correct answer. Here are some interpretations of these scoring guidelines to help understand how points are awarded in this type of a problem, and to help prepare for the next AP Calculus exam. The first point is earned for presenting the correct first step of Euler's method with at most 1 error. If there's only 1 error, and therefore we recognize a legitimate attempt at Euler's method, the student earns the first point, but is not eligible for the second point. Here are some example student responses in which there is 1 error in the first step, but we still recognize this as Euler's method, award the first point, and the student is not eligible for the second. In this example, the student has used a positive 2 as the step size instead of a negative 2. And in this example, the student used the value of x of 12 instead of y of 12. Many students use a tabular method to apply Euler's method, and that's fine. However, the columns really should be properly labeled. If an unlabeled table is presented, we'll still award both points if the student arrives at the correct answer. If the student presents an unlabeled table and an incorrect answer, no points are earned. The second point is earned for the correct answer only. In some cases, if a student makes an error that does not change the nature and complexity of the problem, we'll read with the student to possibly award additional points, but that's not the case here. If the student makes an error along the way, at some point in the process, they do not earn the second point. And, as usual, the final numerical answer does not need to be simplified, but y and y prime must be evaluated. In Part D, we need to find an equation of the line tangent to the path of the particle at time t equal 12. The key concepts here are, first, the equation of a tangent line to a curve at a point, and second, finding the slope of a curve described parametrically. Finding an equation of a tangent line is a pretty straightforward problem. Your AP Calculus students solve this problem in many contexts, starting early in the course. Consider the graph of y equal f of x at the point x sub 0, y sub 0. The slope of the tangent line at this point is f prime of x sub 0. And here's an equation of the tangent line. Suppose we want to find an equation of the line tangent at a point on the graph defined by the parametric equations x equal f of t and y equal g of t. If f and g are differentiable functions, and y is also a differentiable function of x, then we can use the chain rule to find the derivative of y with respect to t. If dx dt is not equal to 0, then we can solve for dy dx. It's just dy dt over dx dt. And dy dx is the slope of the curve. Okay, let's solve this problem. The slope of the tangent line at t equal 12 is dy dx evaluated at t equal 12, which is dy dt over dx dt, each of these expressions evaluated at t equal 12. Or, more compactly, y prime of 12 over x prime of 12. Y prime of 12 is equal to minus 5 from the table. And we can use the expression given for x prime of t to find x prime of 12. So the slope of the tangent line is minus 65 over 12. We have a point on the tangent line, 4 minus 3, given in the statement of the problem, and we just found the slope. So here's an equation of the tangent line to the path of the particle at time t equal 12. And both of these expressions are acceptable. Here are the scoring guidelines for this problem. Part D was worth 2 points. The first point is for finding the correct value of the slope of the tangent line. And the second point is for presenting a correct equation for a line tangent to the path of the particle at time t equal 12. Here are some interpretations of these scoring guidelines. The slope of the tangent line does not need to be labeled. It can appear unannounced as part of a correct tangent line equation. And this type of a response would earn 2 points. Here are some example student responses and how each is scored. In this example, the slope is unannounced, but it appears in a correct tangent line expression. So this earns 2 points. In this example, the student has used the numerical value of the slope, correct to 3 places to the right of the decimal, rounded. This also earns 2 points. And this is just another way the tangent line equation can be presented. This response earns 2 points. If the student declares an incorrect value for the slope, they can still earn the second point if they present a line that passes through the point 4 minus 3, and as long as the slope is labeled as dy dx, and they cannot leave the slope unlabeled in this case, or use m as a label. Here are a few more example student responses to help clarify these scoring guidelines. In example 1, the student has an incorrect slope labeled correctly, and the line presented does pass through the point 4 minus 3. So this response does not earn the first point, but earns the second, or it is scored as a 0-1. Similarly, in example 2, the student has an incorrect value of the slope. This is the y value at t equals 12. But it is correctly labeled, and the line passes through the point 4 minus 3. So this response earns 0-1. And again, in example 3, the value of the slope is incorrect. This student used only dx dt. However, it's labeled correctly, and the line passes through 4 minus 3. This response also earns 0-1. In example 4, the student has not declared a value for the slope using dy dx. The variable m is considered too vague in the context of this problem. So this response does not earn any points. In example 5, the student has presented a numerical value for the slope, correct to 3 decimal places, truncated. Remember that in 2020, students could use technology on any part of the exam. The tangent line is correct. This earns 1-1. And in example 6, the student has declared the correct value for the slope of the tangent line. However, they have not presented a correct equation for the tangent line. In this expression, x cannot equal 4, so this is not a valid way to represent the tangent line. This response earns 1-0. I hope this video gives you a good idea of how to solve these problems using the necessary AP Calculus concepts and a reasonable expectation of how they would be scored. We'll look at more parts of this free response question in the next video.